Hi everybody, this is Waehner from Confluent. Today I want to talk about streaming analytics for IoT data with Apache Kafka and machine learning. I will show you a few very cool architectures for building machine learning infrastructures with Kafka. And for some you don't even need a data lake like Hadoop. Let's get started. In the beginning I want to point out what I mean with event streaming, which I talk about all the time. So with this I really mean that you can continuously process data and analyze the data in flight, while it is interesting. So in contrary to first storing everything at data at rest, like in a data lake or database, you continuously process the data in real time, even if it's high volumes of data. And you don't take just one data stream, but you also correlate it with data from other systems, like other event streams, or like other traditional systems like data from a database. And that's what I mean with event streaming. And then to combine it with machine learning, let's understand what machine learning means. In the end, we see use cases both to improving traditional use cases and to build new innovative use cases. A very common use case which exists forever is fraud detection. We have this for 20 years with some business rules and then with some statistical models. And now with machine learning and deep learning, this gets much more powerful. This is simply where a business process already exists and we improve it. On the other side, we also build new innovative use cases like a chatbot with speech translation. This is something which is only possible because we now can leverage deep learning in a real-time infrastructure. And so there exist many different kind of scenarios where machine learning and event streaming make sense together. I will cover one specific use case here with a global automotive company which builds a connected car infrastructure. But what you will see in this talk today can be really mapped to any kind of industry, and no matter if you're working in financial services or telcos or a gaming company. And the scenario I want to talk about today is that this company already has built a connected car infrastructure. This is something what we did, for example, with Audi already. So you can already integrate to all the cars and ingest and correlate all the data of the sensor information in real time. Because then when you have this as a next step with this foundation, you can apply analytic models from machine learning to even improve some of the use cases or build new innovative use cases which were not possible before. And that's in the end this kind of journey which I want to discuss in this talk. So this is the current status in this scenario. We have a streaming analytics platform, and here we ingest a lot of data from the sensors in real time into the event streaming platform. And from there then we process the data and correlate it and use different consumers. So one of the consumers might be a batch platform where we do classical reporting, which may be running overnight to create some nice analysis and reports and insights. But on the other side, we also have a real-time consumer, which is a real-time monitoring system. So the beauty about Kafka and event streaming is that all these systems are decoupled. So one can consume the data in real time, while the other one consumes it in batch mode. And a third one might be a mobile app where you just click a button and do a request and get the answer via response, for example, with the REST proxy from Confluent. So this is the current status now actually for this project. And now we want to apply machine learning to make it even better, in this case to do predictive maintenance in real time by analyzing the engine, the vibration spikes from the car and all these kind of things. So for that we need machine learning, which in the end means that it allows computers to find hidden insights without being explicitly programmed where to look. That's what you need in these scenarios where you have terabytes of data and need to analyze this somehow. Machine learning is different algorithms, so no matter if you use a decision tree or clustering, or maybe a cutting-edge neural network where you apply deep learning algorithms like a recurrent neural network or a transformer. In our example, we will use an autoencoder to do anomaly detection. To take a look at the vibration spikes of the car engine and then find out if something is problematic and if there is a specific probability that the engine might break soon, so that we can alert the car and the driver so that they go to a repair shop very soon. So if we apply machine learning, and that's the beauty here, we don't have to change our overall architecture and data pipeline. We just add additional components. Because as I said, everything is decoupled. You can simply add new things. And here in this case, in green, we have the analytics platform where we consume the data from the streaming platform in real time. And then we train our analytic model of that, which often still is a batch process. That's totally fine. But we still have the simplified architecture because we don't need another data lake for that. So you could, of course, ingest everything also into HDFS or S3 and then train a model with Spark ML. That's totally valid approach as one option. In this case, we directly consume the data from the streaming platform to have one less component in our architecture. And then when we have trained the model, then we deploy it to another application, which is using this analytic model for real-time predictions at scale for millions of events in real time. And in parallel to that, we still have this other consumer like a batch platform, which does reports for BI. So if we think about our first analytic model, so typically in a Hello World example, you use something like Python and a framework like TensorFlow and have 20 lines of Python code to train a model, and that works well. And this is pretty nice, but in the real world, you have to think about how to deploy the models in production for real-time processing at scale with no downtime and no data loss. And that's a completely different story than just developing some Python code in a Jupyter notebook. Google has published a paper a few years ago about the hidden technical depths in machine learning systems. And here you see that the ML code, this is just a small part of the overall situation, like data collection, the serving infrastructure, monitoring, feature extraction. There's so many big challenges which are much more complex than writing the Python code. Well, and there's already a lot of companies which have solved this problem, however. So they have built a scalable and technology-agnostic machine learning infrastructure. And here just 3 of these examples. Netflix for its recommendation engine, Uber for its ride-sharing services like estimating the estimated time of arrival, the estimated cost, and other things like fraud detection, and then PayPal for payment processing and fraud detection. These are 3 different examples, and all of them have in common that they have to act in real time, at scale for millions of users, and mission critical. So this has to run 24/7 all over the world, and you cannot lose any data here. Well, and this is probably the reason why these and many others use Kafka for building machine learning infrastructures. So let's see how this is related. Apache Kafka is an event streaming platform, and it got the de facto standard in the meantime for processing data continuously. And that works very well because Kafka is not just a messaging system for sending data from A to B and C in real time. It's also storing the data, and with that it's decoupling the producers and all the consumers from each other. So it's no problem if one consumer is doing batch mode or falling behind because it cannot process all sensors in real time. That's good. But another fraud detection application might have the requirements for low latency and real-time processing. And a third app is a mobile app which communicates with request response interactively. With the decoupling and the storage in Kafka, this is possible, and you store everything event-based with guaranteed ordering and with timestamps. So you can process all orders in real time or only when you need some of them. And that's what makes Kafka so strong. And Kafka is not just messaging and storage, but it's also available features like Kafka Connect for data integration to legacy sources and things and to modern sources and things. So this is both for IBM MQ and for mainframes, but also for Flink and for cloud ML services. And you also have data processing capabilities like Kafka Streams or ksql. And this is really what the streaming platform is and why it's used so much. And machine learning infrastructures are one great example for this. So here's how this looks like with Kafka and ML together. ML is always model building and model deployment. So model building is where you ingest the data and pre-process it, and then you deploy a model. That's the second part, where you have a production app where you do the real-time scoring and predictions. And as you can imagine, Kafka and its ecosystem is really perfect for that, because you can use it for data integration and data processing before you train your model. And then you can also use it for model deployment and for all the monitoring infrastructure from a technical and from a business perspective. So let's take a look at that in more detail. When you do machine learning, you first have to ingest all of this data. In this case, it's IoT, but it's true for everything. You ingest the data, for example, with Kafka Connect, into your Kafka cluster, which might run at the edge in a data center or in the cloud, maybe even as a fully managed service with Confluent Cloud. Or it might come from another Kafka cluster. So that's also a very common scenario where you have one production Kafka cluster with very high SLAs for availability and low latency. And then you have the analytics cluster, which might run somewhere else and which often has lower SLAs. So if that one is down for an hour, it might be okay for you. And after you get the data into your Analytics Kafka cluster, you need to do some pre-processing. Of course, you can do everything with just Python code, right? But again, remember the hidden technical depths of machine learning. You need to do that at scale, in real time, in a reliable way. And therefore, for some of the use cases, it's much better to do that with Kafka native technologies, like Kafka Streams or ksqlDB. And maybe you separate it. So you do these normal things like filtering and transformations and anonymization with Kafka native technologies, and then only focus on extracting features for your models with a Python framework, which might be the better fit for that. And after the pre-processing, then you're ready for model training. But for pre-processing, here is one more example where we use ksql. And as you can see here, actually, we even use a Jupyter notebook with Python to combine that with ksql. So in this way, the data scientist can use their favorite tools, but he can combine it with the power of Kafka and event streaming for processing millions of messages in real time at scale. And here's just one example where we do a simple transformation. In this case, it's a filtering, where we have continuous input streams from all the car sensors, and we only filter one specific car type to process the data of that type. But this runs mission critical for millions of messages per second because it's Kafka under the hood, with deploying just this single query without any other code. And after pre-processing the data, then we ingest it into a data store for model training. Like in this case, we use Google Cloud Storage. But again, it's important that this is decoupled from other processes. While the model training is then batch, we can also have the data ingestion in real time into Elasticsearch, or in an InfluxDB in real time for time series analytics, or into a custom C++ or Java application for your next business application. This is one of the strengths of Kafka, that you can consume from many different applications with different kind of requirements regarding real-time or communication paradigm. So finally, after all these steps, we can train our model. This is not Kafka, this is a machine learning framework. In this case, we leverage the extreme scale of the Google Cloud, where we use TPUs and TensorFlow in the cloud to train a model. As I said in our example, we use an autoencoder. We want to detect anomalies in the vibration spikes of the motor engines of the cars while they are driving. So you train your model, this takes a few hours or so, and then you have this binary ready to deploy it. Because it only gets added value if you deploy it, right? So model training is one part. But let's talk about model training a little bit more. So what we just did, we ingested all the data into a data lake. In this case, Google Cloud Storage. This is totally fine and a valid approach, and then you can use Google ML services or Spark ML to train a model. However, I also want to show you one other approach. In this case, we are doing streaming ingestion and model training. This means the machine learning framework directly consumes the data from the event streaming from Kafka. This simplifies the architecture because you don't need another data lake like Hadoop or S3 or Google Cloud Store for that. And with this case, we really directly use TensorFlow I/O to consume from the Kafka feeds. And that is really a great example for simplifying the architecture. And then you can also reconsume the data again. That's the beauty of this log. Everything is event-based with timestamps and guaranteed order. So you can first train two different TensorFlow models with different hyperparameters. But maybe then later you also try another tool, like in this case DataRobot, and evaluate if that's maybe the better one for your use case. There is not just one single machine learning framework for every use case, and so this is a great opportunity to consume the data with different technologies and use the best technology for your problem. So at this point you want maybe to ask, well, should we really store data long-term in Kafka to reprocess it again for model training? And as I said, so you can of course use another data lake, but you can also store data in Kafka forever. That is possible since the beginning. You can have a retention time of -1, or of a year or 5 years. And so sometimes, however, when you store big data sets, this is not ideal, because in Kafka, processing and storage is combined in the brokers. And therefore, this can get very expensive if you store terabytes of data on the HDDs or SSDs of the broker. And also scalability gets an issue when you need to do rebalancing for terabytes of data. This can take not just minutes, but maybe even hours if you have really big data sets. That's why we also can see a simplified data architecture here more and more. And that's with tiered storage for Kafka, which means that you still have this one single infrastructure and architecture with Kafka, but you offload most of the storage into an external remote store, like an object store like S3. And with this, you have the advantage that you don't need another data lake like Hadoop anymore. You can do real-time processing and batch analytics with historical data with the same infrastructure. This reduces the cost and it still has a key feature like performance isolation. So one consumer can consume it in real time and the other one in batch mode for machine learning. So this is really to keep your architecture simple. And so here you see one implementation of tiered storage, which is Confluent tiered storage for Kafka. So in this case, we offload most of the data to an object store. Only the latest data of the last maybe 2 hours is stored on the brokers, not everything, and the rest is offloaded to the object store, like S3 or Google Cloud Storage. The beauty is that from a consumer perspective, the Kafka API does not change. You still consume the data from Kafka, either in real time, or maybe as a data scientist, you say, give me all the events from the 1 month of last year. I want to consume all of them for doing a new data analytics or new model training on that. And with this, you can store data forever in Kafka in a very cost-efficient way because the object store is much, much cheaper than the local broker disks. And the scalability gets much better because when you need to do rebalancing in Kafka, you don't need to rebalance terabytes of data, but only what's on the brokers. And that's then just the last 2 hours, for example, which is just taking a few seconds. There's plenty of use cases for reprocessing historical data in an event-based manner. So here's a few of these examples. Model training is what I talked about in this example, but also it's, for example, if you have new consumer application or want to build a new materialized view of the data in another database or BI tool. It's also for error handling. When you process all the events and then you find out there was a problem in one of my applications, then you fix the error and then you reprocess it again for these events which you processed wrongly. Compliance and regulatory are huge use cases we see all the time, where people need to store data for 10 years. And then at some point in time, you don't know that beforehand, you need to query some of the old data and reprocess it for analytics to prove that you are compliant to a specific issue. So there's many of use cases. While you can continuously process data in real time for some applications, you can also access old events and historically consume them and then process them for your advantages. And now we have trained the model. This is the first part. Of course, model deployment is also important. The good news is it's completely separated from the training. This can be deployed somewhere completely else. A model is just a binary, so you can train it in the cloud, maybe just with Kafka and TensorFlow, or maybe with Kafka and a data lake like Hadoop and SparkML. That doesn't matter. But then the model deployment is really what's the most critical part. This has to run in real time, at scale, in a reliable way. You have different options with Kafka. I cannot cover this in detail here. I had a Kafka Summit talk where I talk about this for 60 minutes for model deployment. On a very high level, you have two options. You either use an external model server, like TF serving for TensorFlow. This has the big drawback that you always do an RPC call between the streaming Kafka application and the model server. This works for some use cases, but for example, in a connected car infrastructure for millions of events, this is not the ideal architecture. Therefore, another option is to embed the model directly into the streaming application. And this can be Kafka Streams or ksql, but this could even be just a C or C++ Kafka client if you deploy it somewhere at the edge with TensorFlow Lite, for example, to do the scoring and predictions embedded into the streaming application. Both approaches have trade-offs, pros and cons, so please check out my Kafka Summit talk about this topic if you want to learn more details about the model deployment. Here's one example of that. In this case, we use ksqlDB again. And here we have defined a user-defined function to detect the anomaly. So the autoencoder we trained before in the cloud is what we embed here. And now we have created a stream for every single sensor event from any car. And we apply the TensorFlow model to these sensor values of the vibration spikes. And with that, we detect if it's an anomaly and if the car will probably break or not. And this query is so simple, but still it uses Kafka under the hood, and so you can process millions of messages with that per second at scale reliably, and you can just deploy this to a ksql server. And this is pretty powerful, I think. And therefore, here's the final overview of this architecture again. On the left side, we have the car sensors, and we can use technologies like MQTT to ingest that into Kafka. And then we do on the top processing with ksqlDB before we train our analytic model with TensorFlow. And then we deploy our model completely separated from that to another analytic model, to another Kafka Streams application, which uses the analytic model. And in parallel to that, we have other consumers, and not all are real time. Like in this case, we might build a digital twin with MongoDB from all the data from the cars. We have also built several different examples for Kafka and machine learning, including this powerful example of the connected car infrastructure. Just feel free to check out my GitHub examples about Kafka and machine learning. So in summary, what we use here, and this is a more provoking statement, but I say one pipeline to rule them all. But the big advantage of Kafka is that you can use it both for real-time streaming and also for analyzing historical data. For example, for model training. And therefore, this is a great example to use one pipeline for model training, for real-time scoring, and for monitoring all this infrastructure from a technical and a business perspective. And that's what makes Kafka so strong and why so many people use it for machine learning infrastructures. I hope this was a good overview about streaming machine learning with event streaming and Kafka. Feel free to connect on LinkedIn or Twitter to stay in touch with me and let me know any questions or feedback. Thanks for watching.